Hello everyone, welcome back. Today I'm going to talk about one more topic from Module 1, that is load balancing concept. What is this load balancing concept is? Uh, to balance externally applied load, provide cable profile in the shape of BMD. This concept is called load balancing method, and we have a formula for eccentricity of the cable, that is E equal to m by P. Just by this statement you will not get a clear idea. So let me show you some load and BMD and the diagram. Here simply supported beam is, I have considered it, and on that UDL is acting for this kind of a load and the beam. Usually, or the bending moment will be parabolic like this, okay, and it is above the beam. But when it comes to load balancing concept, whatever bending moment is there, whatever shape is there, we should give exactly opposite to it, or exactly the mirror of this BMD. We should provide a cable. Here this is nothing but a cable, and this line is a neutral axis. With reference to this, we should provide a cable depending upon this BMD. So this is what they are telling, that to balance externally applied load, provide cable profile in the shape of BMD. Okay, it is exactly opposite of the BMD. We should provide a cable. The second case is simply supported beam carrying a point load. For this kind of a loading case, we get a BMD has triangular variation. So triangular variation is positive here, so it is above the beam. But how we should provide a cable here? It should be exactly mirror of that BMD. So provide the cable towards like downwards, and it should be in the triangular shape. Whatever this E you can see, it is nothing but eccentricity. At this point, how much eccentricity will be there, we should find out. That can be found out by using a formula E equal to m by P. The third case is simply supported beam carrying 2-point load. So for this kind of a load, it's a trapezoidal variation, trapezoidal BMD. So again, at the bottom we should provide a cable in a trapezoidal manner, and E should be found out exactly below the load. So here the first load is there, so below that how much is E, second load is there, below that how much is E, we should find out. This is a fourth case. So you can see overhanging portion here. So the bending moment will be like this. Near the overhanging portion, you can see a variation like this, and it's a parabolic variation at this portion. So you should mirror this for a cable profile. So a cable profile will be like this. Okay, so it is positive above the beam, means in the cable it is below the beam. If it is negative in the BMD, it will be like negative in the BMD, so it is below the beam. But here in the cable profile, it will be above the beam. The next case is the beam will be like this. Only in one portion we have a overhanging portion. So when the beam is carrying UDL with a overhanging portion, BMD is like this. So it is exactly opposite to it, or exactly mirror of it is a cable profile. Okay, this is all about the load balancing concept. So next we will move to the problem. Here we have a first problem, that is a rectangular PSE beam 400 mm by 300 mm has a span of 9 meter. The beam supports 2-point loads 30 kilonewton each at middle the third points. If the eccentricity at the middle third portion is 140 mm, suggest a suitable cable profile and calculate the effective pre-stressing force required to balance the bending effect of the loads. If the resultant tensile stress at the mid-span is to be made zero due to pre-stress, self-weight and imposed load. Calculate calculate the initial pre-stressing force in the cable for the above profile. What they have given is it's a like about the cross section of the beam they have given it is 400 mm by 300 mm and it has a span of 9 meter. So this diagram is not given, remember that. So cross section is 400 mm by 300 mm and the neutral axis is exactly at 150 mm, 300 by 2. Next, length of the beam is 9 meter. It carries a 2-point load. That beam carries a 2-point loads, that is each load is of 30 kilonewton. But where it is placed or what is the location of it is they have specified here, that is middle third points. Middle third points is a little bit tricky. What they meant is it is nothing but L by 3. Here for this beam L is 9. 9 by 3 middle third points means L by 3, that is 9 by 3 we will get 3 meter. So from the left 3 meter at 3 meter distance one load is placed. Again from here to here 3 meter one more load is placed. Like that we have 3 portion on this beam, each of 3 meter. So like this you should divide the length and you should place a loads whatever they have given. And the next part is about eccentricity, and about the eccentricity they have given it is 140 mm at middle third portion. Again this portion is same, I will explain regarding this in later picture. Suggest a suitable cable profile. They are asking for this kind of load condition, how should be the cable profile, we should mention that. And next thing is calculate the effective pre-stressing force required to balance the bending effect of the load. The pre-stressing force should be, P value should be found out to balance the bending effect of the loads. That is second point. The third point is if the resultant tensile stress at the middle span is to be made zero. Please pay attention here, that is they are telling resultant tensile stress at the mid span is to be made zero due to pre-stress, self-weight and imposed load. Calculate the initial pre-stressing force in the cable for the above profile. Actually what they have mentioned is, the first thing is in the second part we need to find out a p value. Again in the third part they are asking us to calculate the p value. Why? That is initial pre-stressing force. Why? Because on what basis we should find out this p is to keep this resultant tensile stress at the mid span as 0. To maintain that resultant tensile strength at the mid span as 0, how much should be the p value, we should find out that. So, resultant tensile stress at the midspan is to be made 0 means F inferior equal to 0. F inferior is equal to 0. Remember that, as this is a point load, it is nothing but this beam will be sagging. Because of the sagging condition, compression will be at the top, tension will be at the bottom. So, resultant tensile stress at the bottom, F inferior, will be 0. By equating this, we should find out the P value. So, next is okay, fine. I forgot to mention about SFD. Here they have not mentioned about SFD, but we should find out how much is a SFD. So, how to calculate this SFD? How did I write this is, please check this note, that is, for symmetrical section in SFD, total load by 2, that gives reaction at support. That means what? As this is a symmetrical section in SFD, if it's a symmetrical section, what we can do is, we can take it as total load by 2. Here, what is the total load? 30 plus 30. These are the external loads coming on the beam. So, it is total, external load, total load. So, it is nothing but 60 kilonewton. So, 60 kilonewton by 2 will give you 30 kilonewton as a support reaction. Whatever answer we get, that is nothing but reactions at the supports. Like this, I have got 30 kilonewton here, 30 kilonewton here, that is 60 by 2, 60 by 2 is 30 kilonewton. That is a support reaction. Next is SFT. See, how to draw this SFT is, at the support reaction at A, we have 30 kilonewton acting upwards. So, acting upwards means it is positive, it should raise from the beam, it should raise above the beam. So, up to 30 I have raised it, and even at this portion up to here it is even, from here to here it is even. After coming to this point, what will happen? This will be plus 30, we have the 30 kilonewton acting downwards, that is nothing but minus 30. So, plus 30 minus 30 is nothing but 0. So, from here again we should go down. So, the variation will be a rectangular variation. Again, this side also it is same. So, the SFD is like this. Okay. So, here the 30 kilonewton, it is acting downwards. So, I have written it down. Then up to here it is same. Then from here it is again plus 30. So, it has raised and it has reached this beam like this, and variation is like this. But always remember, where SF is 0, this in this portion SF is 0, this portion is called as pure bending. From from this 30 to this 30, whatever space we have here, the SFD is 0. This portion is nothing but pure bending. This is about the SFD. Next slide is about a cable profile. Here, to calculate a cable profile or to decide about the cable profile, first we need to find out how much should be the BMD value. So, to find out that, what we have done is, we have written M equal to, that is moment equal to load into the distance. Okay, W into A. Here is, you can see here, in the previous slide I have just mentioned A, B, A. So, like that, or referring to that, I have written W into A, depending on that distance. So, here about W, you should remember one point, as this is a symmetrical section, we can go for W we can go take support reaction as well as a load. Both are same because even support at the support reaction the value is 30, load is also 30, so whichever we want we can take it. But uh, but I prefer always you go for the support reaction value, whether it is unsymmetrical, symmetrical, always take W has a support reaction value. So we know that moment about the support is 0, but under the load how much is a bending moment we should find out. So under the load, under this point, okay, under the load how much is the moment is, it is nothing but 30 into 3. So reaction into 3 will be 90 kilonewton meter for the moment. So to we got a bending moment formula. So it is 30 here, even the 30 here. So value will be same and the variation will be like a trapezoid. So I have written for a bending moment, I have written a trapezoidal variation. At the support the moment is 0, so these points are 0, and from here to here it is 90. So from here to here it is even. So here it is like even. From here to here it is even. Again this will change as it is 0 here. So the bending moment variation is in a trapezoidal manner. But as I told, the load balancing concept depends upon the BMD for the cable profile. So as this is a trapezoid here, the whatever cable profile we should provide, it should be also a trapezoid. This line is nothing but it is just a like to measure. I have written this line, okay, nothing else. So E is comes here. In the question they had mentioned that eccentricity, see, read out this, if the eccentricity at the middle third portion is 140 mm, at this point it is, they are talking that they are saying it is E value is 140 mm. So on both sides under the load eccentricity is 140 mm. So I have written E equal to 140 mm equal to E. This is a trapezoidal trapezoid is a cable profile. The next thing is about see, till here the first portion is over. In the question the first part was to determine the cable profile, that portion is over. The next portion is finding out the pre-stressing force to balance it. So we have that external bending moment. How this will occur? External bending moment occur due to load, and we have a internal bending moment. This occurs due to pre-stress. So what is the external bending moment we have got? Just now we got it as 90 kilonewton meter. That moment whatever we have, bending moment whatever we have got, that value I should consider. So it is 90 kilonewton meter. I have just converted it into Newton mm. So it is 90 into 10 power 6 Newton mm. The internal bending moment happens due to pre-stress, that is given by P into E. So we P is unknown, we should find, but we know how much is the E value there. So it is P into 140. So for balancing, what we should do is we should equate it. Internal bending moment equal to external bending moment. So I have written like this in a short notation. So P equal to M. If we simplify, we will get P value, that is 642.86 into 10 power 3 Newton has a pre-stressing force to balance it. Okay, this is a second part in the question. Again one more is remaining, that is a third part. They had asked to calculate, see here, this is a third portion. Calculate P for resultant tensile stress is 0 at mid span. Resultant tensile stress, how do we decide it is at the bottom? Means I had told, as due to the load we can understand that it is nothing but a sagging case. When it is a sagging, compression will be at the top, tension will be at the bottom. So they are talking about this. So F inferior is 0. So consider that. We already know a standard formula for F inferior, that is P by A plus PE by Z minus mg by Z minus mq by Z equal to 0. So this is a standard formula, and be careful with the signs. So equate it to 0 as F inferior is 0. For these things, what do we require? We require to find out a few things for this formula. So we will start with the area. How much is the area of the beam? That is nothing but 400 into 300 is a cross section of the beam. So we get it as 120 into 10 power 3 mm square. The next thing is we need I value. So I is nothing but BD cube by 12 for rectangular cross section. So width is 400, depth is 300. 1 second. Okay, yes, correct. Width is 400 mm, depth is 300 cube by 12. You will get 900 into 10 power 6 mm per 4. So the next thing is a calculation of sectional modulus. Z equal to I by Y. I have calculated, and Y has, this is a symmetrical section. Y is nothing but 300 by 2. You will get 6 into 10 power 6 mm cube has a Z or sectional modulus. And remember one thing, why I have not mentioned anything about the sectional modulus notation is, I have not written it as ZT, ZB like this, because it's a symmetrical section. In symmetrical section, directly we can take it as Z has ZT equal to ZB equal to Z. So take the notation as Z. Next is a calculation of dead load. For dead load, what is the formula? The formula is area of cross section of the beam into density. Area of the beam is in mm. Convert that it into meter. So 0.3 into 0.4 into density is 24 kilonewton per meter cube. You will get dead load as 2.88 kilonewton per meter has a dead load. Next is mg. Mg is nothing but moment due to dead load. So moment due to dead load is, we have already calculated the dead load value. So take that, it is 2.88 into what is the complete length of the span? It is 9 meter. So 9 square by 8. You will get 29.16 kilonewton meter has mg. Next is mq. mq is nothing but moment due to live load. This we have calculated already, that is external bending moment. MQ or external bending moment, both are same. So consider this, where is it? Okay, this value. So take it as 90 into 10 power 6 Newton per Newton mm has a external bending moment. So all the terms are ready. Now we should substitute in this formula. So we know F inferior is 0. So you can make this term as 0, and here the P value is unknown. We are finding out how much is P. So keep P as it is, don't substitute anything, and be careful while substituting these signs. So it is, yes, here also it's a same formula, even everything is correct here. So substitute these value. Area we have found, E we know, sectional modulus we know, mg and mq. Substitute everything, and make sure you substitute all the terms with the proper units. So we will get P value as 627.15 into 10 power 3 Newton has a P. This P is different and this P is different. this P is nothing but pre-stressing force required to balance it. This P is to maintain the resultant tensile stress has 0 in the midspan. So I have clearly written here P value when tensile stress is 0 at midspan. This is the third portion. We have first portion is over, that is nothing but cable profile. Second portion is what to find out P value to balance the section. The third one is to maintain the tensile stress at the midspan as 0. We have got P value. So till here everything is fine. We are done with the problem. Thank you.